In one of our last synthesis videos, we're looking at chapter 19, and we'll address some of the kind of larger topics of synthesis and really some language associated with it. So if we were to look at a lot of our kind of organic reactions, particularly carbon lengthening or chain lengthening reactions, carbon's typically going to come in with a positive charge. And that becomes problematic because I can't get those two similar charges to react with each other. They're going to be a no reaction. So to get them to react, I'm going to have to somehow change the charge on one of them. So for instance, with the reactions shown above, we could take advantage of, say, a Grignard, and that Grignard reaction would insert the magnesium into that bond, and we would now have a negative carbon. And I should draw a negative carbon. So that change in charge for that individual carbon is what's now allowing us to now react these two structures. Right? And so that process by switching charges on an individual carbon is what's known as the Umpelung change. Okay, so polarity reversal. A lot of the reagents we talked about in this particular unit do that. Grignard does that. The Wittig does that. Those are the two that jump right out at the top of my head. Our Gilman does that. We're looking at switching that charge. So you may hear people refer to an Umpelung because what it's doing is just changing the charge and activating it for a forward reaction process. So our Grignard is a perfect example of that. We just looked at the Wittig. There isn't a whole lot for me to add there. But what is important to note is that we get lots of carbon-carbon forming bonds, okay, or forming carbon-carbon bonds. Our textbook does a really good job of providing these tables, both within the chapters that we're talking about them and at the end of the textbook. So you should take advantage of those to note those and kind of call out to them when you're going through and doing a synthesis. You are not expected to hold all of those reagents at the back of your mind every time you attempt a synthesis. And that's something that's challenging for a lot of people to kind of acknowledge. You are responsible for looking them up. And even as a synthetic chemist, you would be looking up a lot of these reagents, allowing you to do it. The more you have memorized, perhaps the faster you could get through your design of synthesis, but you're going to spend the vast majority of your time looking at literature and finding these reagents. So when running a synthesis in this class, particularly with the homework, that should be your focus. Have the textbook with all those different syntheses or reagents available, and when you look at a synthesis, be like, that bond is a good bond to break, or that bond I need to make. How can I make that? What functional groups would allow me to run that process? And that's where you would dig back to your synthesis reagent lists. The SmartWork allows you to sort of simplify that because they limit what reagents you're allowed to use. Okay, but it's still challenging. It's probably one of the most difficult aspects for a synthetic chemist. Okay, one of the other big concepts that's going to come out of this is this idea of selective reactions. Depending on our reagent, we could get different results. And we've seen this already as we've moved through. We've used this term. And so when we're picking out reagents, one of the things that can be helpful is making sure that we pick reagents that only allow one type of reaction. Okay? So if we were to look at the two reactions up above, sodium chloride would be a great reagent for a substitution. Whereas if I used something else in that solution, that could have allowed some other result. If we move for the selective reagent for elimination, we're using T-butoxide in this case. That's a stupid strong base, or not stupid strong, that's just a strong base, so that should facilitate an elimination. But why not use something like hydroxide? Isn't hydroxide also equally strong as T-butoxide? Yeah, it is. But hydroxide also acts as a nucleophile, which means that if I used the hydroxide, I would have gotten the targeted product, and I could spell and I would have gotten the substitution. Okay? And arguably, in this case with that substrate, I would have gotten a lot more of the substitution than I would have gotten of the elimination. Okay? So when you're picking reagents, there are cases where multiple reagents will work. You just have to acknowledge that sometimes a reagent that you see in a reagent list may show up in multiple different places, and so you have to be a little bit more careful behind how your reactions work. And that's a challenge, but that's what makes synthesis kind of interesting. Similar examples, if I wanted to go through and alkylate that starting ketone, I could pick different alkylating or different bases to result in different spots being alkylated, and they'd be selective for that alkylation. How are we selecting between those? Well, that selection between those is ultimately coming back to kinetics and thermodynamics. This base is a thermodynamic favorer, okay, because it was reversible, which means if I use that base, the enolate that I get puts the negative charge out here, so that when I move to the next step, I put the methyl group at that position, and that position only. Okay, this reagent, you might be like, well, dang, we never saw that before. Focus on the chemistry that we see. The nitrogen is negative, the lithium is positive. Negative nitrogen, that's a stupidly strong base, okay? Because it is stupidly strong, it's going to favor doing the enolate in the kinetic spot, and I'm going to end up getting the substitution going the other direction. Okay? Do I need to know the exact specifics of what all of this stuff is? Probably not. Okay? We don't need to know that. What we need to see is where that chemistry is located. So look for those polar bonds. Look for the charges that are shown in it. Look for the metals. Okay? Look for the electronegative elements. It's trying to zero in on those pieces and come up with an idea of what that reagent is likely to do that you need to be focusing on. Okay? The absolute reagent itself could be a really dodgy thing because you would have to have that memorized, and that can be challenging, particularly if you've never seen it before. Okay? So last kind of example that we'll look at here, because I expect you to watch the oxidation and reduction video in PlayPosit that just is the rest of this content. If we were to try and synthesize propylbenzene, we do have a limitation in this particular synthesis. We're only allowed to use 8 or fewer carbons. Okay, so we could go through and say, well, here's 6, 7, 8. In this case, I want to bring on 1 carbon. How do I make that 1 purple bond? Okay, that's following to the letter of this system to try and establish that. I may decide that an easier bond to make would be a little bit further back. Maybe I want to make this one. Okay, that decision is something that you kind of have to own as you move through this. Okay, so let's take a swing, because when I look at this, I think I want to see that. I want a little bit more carbons in my structure. So if I was to make that, I need to connect those 2 carbons. Okay? One way to do it, carbon-carbon formation, would be a Wittig. Okay? So let's take an attempt at a Wittig reaction for this. Okay? For those of you being like, but a Wittig ends in a double bond, that ultimately doesn't matter because we can do other reactions with this. Okay, so if we split this out, whoops, I know what I wanted to do. Wittig would say that what I'm starting with would be the double bond in between. Okay. Again, I'm trying to highlight some of that chemistry so that I can see that differentiation. Okay. Well, I don't necessarily care how I go from the double bond to the single yet. I just need to be aware that there is a way to do that. Okay. And as long as I'm aware that there's a way to do that, then great. Okay. So now I could think backwards. Okay. If we split that, We would need to break those apart. I would need a halide at one, so I could do the halide there, and I would need the carbonyl at the other. Okay? The reagents, as I'm running the Vidig, for me that would probably be enough for me to know all the pieces behind it. So our Vidig, we need the PPH3, we need butyl lithium, and then the third would be that ketone, which is already there. So I would just write own for my own sake. That's going to get me to the Vidig. Now to go, and this is now moving this direction, to go from that Vidig product to the final product, well, that's an addition reaction, and what I'm doing is adding hydrogen across that nonpolar pi bond, so that would be just H2 and platinum. H2 and platinum isn't going to affect the aromatic ring, and I now have a potential synthesis. That could work. Okay, are there other ways to go through and do it? Yeah. Okay, and that's part of synthesis, is trying to test those ways out and see how they function. Sometimes there's very clearly a better way to do it. Sometimes there isn't. When it comes to exams, what I want to see is a valid way to move through it. And if the reagents you're throwing at me, I'm like, where did those come from? Or why would you even think to use those? I may have to dig out and look to see if there's ways to do that. And it's possible there are. Okay? So don't stress about that. Focus more on picking up the pieces that you need to build a synthesis. Okay? Where are those connections or breaks? And then start saying, what do I have? What do I know already that allows me to do that building forwards? Right? It's a challenge, but I have every faith that you can pull this off. You just need that practice with synthesis. So do I. So do I.